Let's explore constructing queries using Lucene and Kibana Query Language, KQL, to view relevant data. Lucene query syntax, Kibana's original search language, shares many capabilities with KQL but uses slightly different syntax. Use Lucene when KQL doesn't provide needed functionality or for advanced features like fuzzy searching, proximity searching, and regular expressions. Each field's data type dictates available searches and operations, indicated by icons in Discover's available fields. Common data types include date, which enables time range searches, for example, timestamp, numbers, which include integers, like long, and decimals, like double. Strings are text data, and IPs enable CIDR notation searches for IP address ranges. Strings are broken into text or keyword types. Text fields undergo analysis during indexing, breaking strings into individual terms, like tokens, through tokenization. This suits longer, unstructured strings like user agent strings or fields requiring individual word searches. Text fields require more index resources and may search slower. Keyword fields remain not analyzed, indexing the entire field value as a single token. The original string stays intact, requiring exact, case-sensitive matches. These can be aggregated and sorted. Use text fields for free text search and keyword fields for exact matching. We can have the best of both worlds using multi-fields, and this is where we can index strings as both text and keyword type. This gives us the ability to search the same data in different ways. With text type, we can use that full text search, and then the text fields are going to be analyzed and broken down into individual terms. Then again, you're going to use a keyword for an exact match, and then you can aggregate and sort the field values. Now strings are normally indexed as a keyword type by default, and then the text type is going to be indexed as a multi-field, and you can see the addition of this .text after the field name. Let's show you a demo of this in Discover. If I type Windows in my query bar, you can see, highlighted everywhere, it says Windows. Let me expand a document here, and I'm going to search for user agent. Notice that Windows is highlighted in these .text fields. You'll see that this user agent string is also the same value as this user_agent original. But it didn't match that because this is a keyword field. To match, I would have to have this exact match of this user agent. Now you can search for any phrase or word in the query bar, and it's going to be analyzed within those .text field names. Full text search is a powerful way to search through large volumes of text data and find relevant results based on individual words, phrases, or even partial matches. This is useful when we're interested in only a small part of that value. Examples of fields that are analyzed are user agents. User agents provide information about the software and hardware being used to access a website. Also, another example would be DNS queries. The values of these fields can be quite long. Maybe we just want to find a specific version within a user agent string or just a specific substring of a domain in a DNS query. Full text searching requires more index resources and can slow down search speed. Searching for a specific field name and value is going to be a lot more efficient than using the query bar like a Google search. Field matching leverages Elasticsearch's indexing to optimize search speed. Here we're using a field value pair where we have the field name and then a colon, which is going to be like an equal sign followed by the value. Here are some examples of field matching where I'm looking for an exact value match. Here's entries from the Zeek conn log. This is a connection log, and the conn log is one of the primary logs and it tracks network connections. Zeek can organize logs by network application layer protocol like HTTP and DNS, but event.dataset is going to be one of the main fields we search for to narrow down the type of Zeek log we want. Let's show you this in action in Discover. Right now we are in KQL syntax. You can see that within the query bar. As I start typing, it's going to give me some suggestions, for example, event.dataset. I can go ahead and click that. Then it's going to give me options of equals. Some value exists in any form, but I'm going to use a colon for equals, and then I want the value of conn. Right here at the top, I'm going to select conn. Now quotes aren't necessary. If I update that, I have a result of 31,972 documents. If I get rid of these quotes, I'm going to get the same result. This is a keyword match. That means I have to have the exact value, and this is case sensitive. If I were to do con in all caps and update that, you'll see that no results match my search criteria. However, this field is a multi-field because it does have a text value as well. If I do event.dataset.text and then update that, you can see that it does match on the lowercase con. The next example is log entries where the server or responding port is 5353. Let me show you what that looks like. I'm going to do destination port equals and then the value of 5353. That brought me to 14 results. Let's say that I wanted to pull the destination port as a column. I can search the available field names. I see the destination dot port here. If I click on it, 100% of my results should be 53 since that's what's in my query. And then if I want to add that as a column, I can see that's added down here. You'll see all of this should be 53. In this last query, we are searching for an event ID to correlate between events and then pivot across different Zeek logs. This is called a unique identifier. Let me show you this in action. Let me pull out an HTTP log, event.dataset. I want to see HTTP. I'll update that. Now I'm going to get rid of this destination port column. I don't need that. If I expand a document, I can go ahead and search for that zeek.session, and you can see _ID. I'm going to copy this value and then back in my query bar, I'll type in zeek.session_ID and then paste in that value. Now what I can do is search for event.dataset in my available fields, and then I can see that this session ID was found in my connection log, my files log, and my HTTP log. This is what we can use to correlate between these logs, and this is one network session. These are all related. Boolean queries or operators are used to combine multiple search criteria and control the logic of your queries. We have and, or, and not. And is going to narrow the search by requiring all the conditions to be true, or is going to require that at least one condition be true, and not excludes documents that match a particular condition. You can use parentheses to group values. For example, if you're searching for multiple values for the same field, this is going to condense your query, and then make it easier to read. You can use parentheses to control the order of operations and booleans inside. Parentheses are going to be evaluated before the operators outside parentheses. The best practice is to always uppercase Boolean operators to make them easy to read. They are case insensitive in KQL, but they are required to be uppercase in Lucene. Here are some examples. Notice that the not is going to come before the field value pair. When you're using and, or, that's going to go between the field value pairs, and then for grouping, again, if the field name is the same, but you want to search for different values, you can put parentheses around those values. Parentheses control the logic and order of operations. Whatever is inside the parentheses are going to be evaluated first. Let's take a look at some examples. Here we're looking for entries from the ZeekCon or HTTP log, and let me show you that in Discover. The event.dataset is a field name. I'm searching for two values within this field name. What I can do is use parentheses to group them together. I'm going to do con, or is going to be my Boolean HTTP. At least one of these must be true. I get 50,000 results back, and then if I want to verify, I can search for event.dataset in available fields. I can click on that, and you can see that my values are going to just be returned as con or HTTP. Again, we can add this field as a column by clicking that plus sign, and then you can scroll down and see what documents correspond to that event.dataset. I want to show you that parentheses matter. If I take away the parentheses here, so this is saying event.datasetCon or HTTP. Notice that the count of documents increased to 63,000, and if I look at event.dataset, I just was expecting it to be con or HTTP, but now I see that there are files as part of the event.dataset, and this is because we're looking at event.dataset is con. And it's treating HTTP like a full-text search. HTTP here is found in event.dataset, but it's also found in network.protocol. You're getting unexpected results. So remember, use parentheses, they matter. The next example here is log entries where the protocol is HTTP and the port is not 80. Here we're using negation with that not Boolean. This looks like we're looking for HTTP traffic that's not using the default HTTP port of 80. I'll show you what that one looks like, and I'll copy this over. I have over 17,000 documents that were returned, and I like pulling out the field. So network.protocol is HTTP, then destination.port. I didn't want to see 80, so the rest of my results are 443. We have HTTP traffic going over port 443, which is a little weird. That's something I want to investigate further. The next example is taking the last query a step further. If port 80 isn't being used for HTTP, what protocol or service is it being used for? Here we want to catch those mismatched ports and protocols. This could be saying services are either misconfigured or intentionally running on different ports or protocols to avoid detection. We're looking for the same query here, HTTP and not destination port of 80, or it is running on 80, but not over HTTP traffic. I have over 17,000 results returned. The destination port is going to be 443, and let me add that as a colon as well as network protocol. You can see if the destination port isn't 80, I have a network protocol of HTTP, but let me scroll down to see if I get any results. I'm not finding what I'm looking for, but if I didn't have a network protocol listed, this would be a destination port other than 80. Let's switch back to the slide to show you a visual representation of that to make it more clear. This visual represents our query. While any service can run on any port, standard ports typically handle specific protocols. HTTP traffic on port 80 is expected. HTTP on other ports deviates from the norm, possibly indicating anomalous behavior. Conversely, filtering by port number reveals unexpected protocols, like port 80 running TLS, instead of its usual port 443. Wildcards match any character any number of times. Now this is resource intensive. It's not efficient, but it's nice to have in your back pocket. Wildcards can be used in part of the field name or the value. This example is searching url.domain for any value that ends with .com. Now to find a value that might exist anywhere in the field name, you can actually add a wildcard on both sides. This can be an expensive search, and we can do it in our environment, but I wouldn't recommend this in a production environment. Let me show you what that looks like. That query was url.domain. I'm going to use a wildcard.com, and I'm going to get rid of these columns here, and then I can get kind of a quick glance of those domains. All of these domains are ending in .com. Then I'm going to show you an example of a wildcard on both sides. Let's say I want to search for Amazon within the domain name, wildcard Amazon wildcard. This should be catching, like all subdomains, maybe like shop.amazon.com or oz.amazon.com. Again, this is an expensive search, so I don't recommend doing this in a production environment. For the next few slides up in the right corner, you can see what the Lucene query would look like, and you'll need to escape wildcards in the field names using a backslash. We can use field exist and leverage wildcards to search for specific field names, to see if it exists in the data. Here are the results from the DNS.log where the DNS answers field is empty. This means that DNS events did not return any domain names in the DNS response. Empty DNS responses can sometimes be a sign of suspicious activity, attempts to communicate with non-existent domains, or some other malicious behavior. This can be used to detect anomalies in our network traffic. We're looking in the DNS log for Zeek, where it doesn't have any DNS.answers.name. You can see it highlighted the event.dataset, and then if I type in DNS.answers, this should be empty. No field data for your current search. This is working as intended, 561 events returned. I would try to investigate further why those events don't have DNS.answers.name value. With the Lucene query, it's going to use _exist_ followed by the field name. We can search for individual IP addresses or do a range search with CIDR notation as long as it is mapped as an IP data type. Here we can do an exact match for the source IP. We can do an IP range. Let's say that this is my internal network. I can do source.ip, this 100.0/24. Let's show you what that looks like here. Searching source.ip with internal range returns 73,000 documents. If I search under available fields and add this as a column, you can see all the documents returned are coming from my internal network. Let's expand this real quick. You'll notice source.ip. We were able to use that CIDR notation because it's mapped as an IP type. Notice that the value of this .54, it's going to be the same value for the source.address. But source.address is a keyword type. I'm not going to be able to do a CIDR range for that. If I did source.address and update it, it's not going to work because of that keyword type. It's not mapped as an IP. For the last query, the search is for internal to external traffic. Again, let's say that this is my internal network. I don't want my internal network to be the one responding. Let's show you this in action as well. I already have my source IP pulled. Let me add destination.ip as a column. You can see my source IP, which should all be coming from my internal network, and then destination IP. These are all external IPs. Now I want to show you another way to use this query. We can use the network.direction field name. Instead of saying source IP of my internal and not destination IP of the CIDR range, I can just do network.direction of outbound and then update it. Those are going to give me the same results, and then we have the ability to do inbound. That's coming from external to internal. We can do just internal. You can see from my internal network to another IP in my internal, or we can do external. With the Lucene query, you're going to escape that CIDR notation / by using a backslash. Numerical field types support comparative operators like greater than, less than, and equal to, as well as numerical ranges. Exact matches use field name followed by a value. KQL comparison operators omit colons. For example, source.port is greater than 56,689. Source.port is less than or equal to 56,689, or the range of source.port is greater than 20 and less than 100. I'll now get rid of the source and destination. I can add source.port as a column, and the column shows values between 20 and less than 100, with matching values of 68 and 42. Lucene does use colons. You can do a range of, including these numbers, with square brackets, and then if you use curly braces, which will exclude the values here. Lucene supports regular expressions for pattern matching. This only works in Lucene, so you will have to disable KQL in the query bar. Use the field name with a colon, encapsulating queries in /. For example, we want to search for the HTTP request method that indicates a client action type like GET, POST, PUT, or DELETE. Then this is looking for GET in either lowercase or uppercase or mixed case. Right now I'm in KQL. To change, I'm going to go to the query menu. Under language, I'm going to switch to Lucene. Now in the query bar, it says filter using Lucene. And a telltale way of knowing I'm in Lucene is as I'm typing. It's not going to give me those suggestions anymore. Let's take a look at that Lucene query of the request methods. Let's paste that in here. I have 17,000 results back. And then I can search for that field in available fields. All of our values seem to be all uppercase gets. Now this query is searching for DNS answers that are formatted like IP addresses. This is a regex query for that. It looks a little complicated, but basically we're looking for digits 0 through 9, appearing 1 to 3 times and then followed by a period. We want to repeat that 3 times and then with that last octet. Digits 0 through 9 appear 1 to 3 times. This represents an IP address. We're still in Lucene. We're encapsulating our regex within those /. I'm going to click Update. Then I can pull out the DNS.answers.name field, and you can see that there are some IP addresses that match within the DNS.answers.name. Fuzzy search is used for approximate matching of terms. This is going to help find documents that contain terms that are similar to the query term but might have some slight differences. This could be like typos, misspellings, or variations of the word, and this can help identify suspicious or malicious activity that might not match the exact search terms, maybe due to obfuscation or intentional or unintentional variations. This does use the full text search with the .text fields, and you're going to use the tilde at the end of the value. There are some caveats here. In order for a fuzzy query to work, the term does need to be at least 3 characters long. If the term is 3 to 5 characters, it's going to look for one difference. If the term is greater than 6 characters, it's going to look for 2 differences. But 2 is the maximum of differences it'll look for. We're looking for terms that have differences by having maybe a character added, removed, or replaced. This query here is finding terms that are similar to Mozilla but are not exactly Mozilla with the user agent string. This could detect modified user agents. Attackers might modify the user agent string to obfuscate their identity, and they're hoping that you just won't catch it. Let me copy this over to Discover to show you what this looks like. We have the field name of user agent original.text, Mozilla, because that's going to be part of the user agent string, and then a tilde. We don't have any matches in our dataset, so this would be finding something like Mozilla. But let me get rid of this and not. Let's say I changed the O to a 0. Let me update that and get rid of this column. Within the user agent original text, I think all of my documents are Mozilla, which is correct, but this is meant to capture any differences within Mozilla. Then we have proximity searches, and this works by looking for terms that appear within a specified distance from each other. This is useful for identifying phrases, sequences of actions, or behaviors that may be indicative of an attacker's malicious behavior, even if the exact terms or patterns aren't perfectly matched. This uses the full text search with the .text fields as well. You encapsulate the search terms in quotes, and then you're going to add a tilde with the number after the search terms. This number is going to specify the distance of tokenized terms after the first match. Here we want to find a user agent string where Windows and x64 appear within 5 tokens of each other. Here we have Windows. We have NT as a token, 6.1 as a token, and Win64 as a token, and then finally that x64 that we were looking for. This appears within 5 tokens between each other, but you'll see that there are 3 tokens between Windows and x64. I can change this to 15. It's still going to work because it's within 5 of the distance. As I make it smaller, 3 is going to be the minimum, and 3 represents the tokens between Windows and x64. If I were to change this to 2, it's not going to work. That can be a little confusing, but what I like to do is this number specifies the number of tokens between what you're specifying, Windows and x64.